I want to talk to you today mostly about supermassive black holes, and in particular, how they have moved from the realm of the imaginary, the enigmatic, to being real astrophysical objects. So what I'm hoping to do in my talk today is to give you a bit of a primer and bring you up to speed on where we are currently with the science. So what is intriguing about black holes, other than the fact that they are largely invisible on their own, is the fact that the name, the phrase black hole, actually originated well before the idea of a black hole came to be mathematically and astrophysically. And the phrase black hole actually derives from a prison, a place in India, the Black Hole of Calcutta, where the Nawab of Bengal imprisoned a bunch of soldiers from the East India Company, and it was a dark dungeon from which they did not exit alive. So the concept, the attribute that we give to black holes, that it's a place of no return, actually came from a physical place. And this was in 1753 or so, right? And the concept of the black hole, of an early concept of the black hole, was dates to late 1700s and was proposed by John Michell, who was a man of the cloth and a scientist at Cambridge. And what he came up with in the context of the Newtonian theory of gravity, where light was believed to be made of particles, corpuscles, as it were, he imagined that you could have stars that were so massive that they would attract light particles completely, prevent them from propagating, and therefore be dark stars, right? And this was, of course, very much in the context of classical Newtonian gravity. And the French mathematician Laplace had a very similar idea as well of dark stars. But what really started off the concept of black holes as we know them today is a fundamental reformulation of the theory of gravity that Einstein proposed. So before I move on to that, let me just give you a brief outline of what sort of a map of my talk, as it were. So I want to talk briefly about black holes, their properties, the cosmic context in which black holes form, grow, and evolve, the observational evidence for black holes, and it's very persuasive and incontrovertible, I would say, and how the first black holes formed, how they actually grow over cosmic time. And then I want to focus a little bit more on the detailed science of what we know about how black holes grow. The fact is they grow, we think, in two different modes, a fasting mode and a feasting mode. So I'll give you some properties of black holes in terms of which state they are in. And then I'll close with how we test our current models, what kinds of observations would allow us to test these models. And along the way, I will mention some of the open questions. So I just want to, before I move on, acknowledge all my collaborators, my colleagues in the field, and NASA for an absolutely wonderful simulation movie that I'm going to show you. I'm going to show you many simulation movies. There's one that's just superb. So I want to thank NASA in advance for the graphics. Okay, so before I move on to give you a primer on black holes, as it were, the cosmic context, there are a couple of things about the universe, in particular light propagation in the universe, that I want to stress. So first, only a finite portion of the universe is observable to us at any time, and that is limited by the age of the universe, which is 13.8 billion years today. That's counting from the Big Bang, and the speed of light. That combination allows you to see out to what is called an observable region of the universe. And as time goes on, more and more of the universe will come into view. But the question is, more distant objects, the relevance for this is because more distant objects, we are seeing them as they were when the universe was young. So when we see a distant quasar that formed, that actually comprises a growing black hole, we see it as it was 12 billion years ago. We don't know what it looks like today. This is important when we try to build a storyline for black holes as to when we need to have the first black holes in place. That timeline is set by the most distant objects that come into view. And the other quick interesting fact is about light propagation, just to give you a feel for how light propagation works in a sort of expanding universe. I have this little graphic that shows you that if you have light rays and you can look over time, if the universe could be modeled as the outside of a sphere, then you can see how light rays probably get stretched over time. So you have a redshift, you have their wavelengths lengthen over time. And what I have in the small graphic there is to just situate you about what we know about the universe today. So we believe that we started off with a Big Bang about 13.8 billion years ago. And after an era of a dark era, before the first stars and the first black holes formed, you had a dark epoch, then you had the first stars and the first black holes turn on, then galaxies assemble in a hierarchical fashion, which means by merging of little bits. So you formed lower mass galaxies that then hierarchically merge to give you higher mass galaxies. And this is important because this is the context in which we want to understand black holes, how black holes actually grow, given that it appears, at least from the nearby universe, that every galaxy in our vicinity seems to harbor a central black hole. Right? So the assembly of the galaxy cannot be, and in fact is very deeply interlinked to the assembly of the stars and the assembly of the dark matter in which all of this action happens. So first, let me spend a little bit of time trying to explain to you how to think about a black hole. So one of the easiest ways to think about a black hole, which is an extremely compact object where matter is very, very densely packed, is to go back to this notion of gravity and escape speed. So there's a notion of escape speed, of the velocity that it takes to escape the gravitational pull of a body of given mass m. And this escape velocity, if a test particle, a rocket, for example, exceeds this escape velocity, then the object will exit the gravitational pull of this body. This is somewhat relevant because it turns out that the escape velocity from a black hole is the speed of light. And what that tells you, and this is the common understanding, that not even light can actually escape a black hole. So for example, to escape Earth's gravity, we need to accelerate the rockets that are constantly being sent out from Florida, Cape Canaveral, or Baikonur, or wherever, 24,000 miles per hour. So that's the kind of escape velocity from the surface of the Earth. And the escape velocity from the surface of the sun is much more massive than the Earth, it's still only about 1/250th of the speed of light. So the speed of light is a pretty enormous number. As I said, it's a small number when we think about the age of the universe and so on, in terms of determining the observable extent of the universe. But the escape speed from even the sun is nowhere close to the speed of light. So as I said, the one way to think about black holes is to think of their gravitational field and the potential to escape from that field and what kind of velocity it takes. The other way to think about it is the packing of matter, how densely you could pack matter. So black holes matter is packed more densely than nuclear state of matter. Okay? But the real way to think about black holes is what Einstein taught us. And he did so by formulating an entire new theory of gravity, which is quite different from Newtonian theory. In Newton's theory, gravity is the force of attraction between any two objects separated by some distance d with mass m1, and this force of attraction is proportional to the product of masses and 1 over distance square. Newton doesn't tell us how this force is mediated, right? It's instant. So two objects with mass will instantly feel each other's gravitational pull. Einstein's work on special relativity showed us that there was a cosmic speed limit, which is the speed of light. Nothing can travel faster than the speed of light. And therefore, if any force field had to propagate, it would be limited by the speed of light. So after special relativity, Einstein came up with general relativity, which actually completely reformulated the whole notion of gravity. It was no longer seen as a force between two objects. It was actually seen as a fundamental connection between geometry, contents, matter, and fate. And so in Einstein's conception, what mass actually did, the attribute of mass, was that it caused a divot or a distortion in the fabric of space-time. So he came up with this four-dimensional entity called space-time, which is the universe, and in which to describe any event, you needed four numbers. You needed the location where something happened as well as the time where something happened. And so the way to think about it is to see how, in this kind of formulation, mass tells space how to curve, and space tells mass how to move, because the undulations that are produced by the presence of matter dictate what motions are permitted. So this is the only equation I'll really be showing, but it is such a beautiful equation that I cannot resist showing it, right? So these are Einstein's equations. There are actually 10 equations that have been short formed into this form. And what was profound about what Einstein did was this connection with the curvature of space-time, the shape of space, if you will, the mass energy content, so the distribution of masses, and the actual fate of the time evolution of this very dynamic system, right? And so key to general relativity are the descriptions that enable the properties of the entire universe to be described, the propagation of light in the universe, because now you have a space-time that is undulating, and light obviously is going to track these divots, these undulations, and therefore will be deflected along the way when it reaches us from distant points when you have mass distributions in between. This is all relevant because a black hole is a particular kind of solution to Einstein's equations. It's a peculiar solution that corresponds to the space-time curvature produced by a point mass. Okay, so that's what a black hole really is mathematically and how it's linked to Einstein's equations. And the fact that the shape of space-time dictates the kinds of deflections of light that are produced is a key ingredient in our understanding and actually rendering black holes visible, if you will, as we'll just see. And so these equations, Einstein never thought would have exact solutions. He assumed that there would be some sort of, approximate solutions, and he proposed this in 1915 in a set of lectures he gave at the Prussian Academy of Sciences in November. So it turns out that a few months later, Carl Schwarzschild, who was looking for a very talented physicist and mathematician, was looking for solutions, chanced upon the first exact solution. So the first exact solution to this equation that was found was that of a black hole. It's a black hole solution. And so the black hole solution corresponds in sort of this graphic that I'm just showing you, the effect of mass on space. So when you have an object like the sun, you have sort of a gentle undulation. When you have something like a neutron star, which is much more dense, notice the curvature of space-time, the divot is deeper. And when you have a black hole, it's practically a puncture in space-time. So this is the solution that Schwarzschild found, okay? So mathematically, this is the conception of what a black hole is. It's the concentrated mass and the kind of impact that it has on space-time. Coming back very quickly to the power of general relativity, right? So in terms of the universe, the contents, the geometry, and the fate of the universe are interlinked. That's something that Einstein's equations show us. So for example, one of the interesting solutions for the universe corresponds to expanding universes, right? Just to set the cosmic context. So let's now look at light deflection, because although black holes themselves do not emit any radiation or reflect any radiation, they do very peculiar things because of what they do to space-time in which light travels, that it is instructive to see how light propagates in space-times. So this was actually predicted, these sort of deflections due to the presence of mass and the deviations in the curvature of space-time, the way in which masses distort the shape of space affects how light propagates in the universe. So light from distant galaxies, for example, would be distorted, which means we don't actually see the real shapes of distant galaxies. We see a systematically stretched out shape, for instance. Now, in the case of black holes, there are even more peculiar phenomena with light that we will just see. So Einstein's theory of general relativity was proved. It made a prediction of deflection of light. And the first proof of it came in 1990 with the solar eclipse, when you can imagine that you have when the Earth and the sun line up, The curvature that is caused by the combined mass of the sun and the earth lining up causes the position of stars to appear to be displaced from where they really are because of light deflection. And this was measured, and Einstein's theory was ratified. So let's come back to the Schwarzschild solution for black holes and look a little bit more in detail about the propagation of light right around a black hole. So we will just see in a minute, there are some characteristic numbers and scales for a black hole. So qualitatively, looking at this graphic, you can see that one characteristic size scale for a black hole is called the Schwarzschild radius. And this is the event horizon. This is the point of no return for a black hole. So the singularity, the mathematical singularity, is encased inside this radius, right? And it turns out that there is an outer radius called the photon sphere, where basically light rays, if they arrive there, can get trapped. They can get trapped and light can orbit around in a stable fashion. And this is interesting and peculiar because what this allows you to do, if you can imagine me standing at that location, which would be extremely unsafe for me to do, but if I did do that, you would see the image of the back of my head. Right? And this is an effect that was exploited very beautifully recently in the movie Interstellar. You might have seen that. You could see the backside. So let's look at a couple more definitions that are important to understand the basic properties of how we think about a black hole, about astrophysical black holes. And as I said, I'll be focusing mostly on supermassive black holes, which are black holes that have masses in excess of 1 million times the mass of the sun. And I'm going to show you they exist. Not only do they exist, but they're actually not all that rare either, especially in the distant universe. So as I said, there are sort of two sort of scales that are important. First is the Schwarzschild radius. This is the radius, the point of no return. And the Schwarzschild radius is proportional, the scale of that is proportional to the mass of the black hole, directly proportional to it. And it turns out that this number is 2 gm over c squared for a black hole that's not spinning. For a spinning black hole, the Schwarzschild radius is a little closer in than it is for a non-rotating black hole. The other important, astrophysically important size scale is the so-called region of influence of the black hole. So for example, our galaxy contains a black hole that is few million times the mass of the sun. Although that is small, the mass of the stars in our galaxy is many orders of magnitude greater than that. However, there is a small region in the inner nucleus of the galaxy where the black hole can exert its gravitational influence. Beyond that, the stars in the galaxy take over in terms of being the dominant gravitating mass. And this region of influence is relevant because we will see one way in which we have detected black holes is the kinds of influence they exert on their environment, on the stellar population in the environment, okay? And so this region is called the region of influence, and that's just also proportional to the mass of the black hole. But notice now that it's proportional to gm over v star squared. So that's the typical speeds of stars in that region, in an inner region. It'll become a little clearer when I actually start showing you some data and models, what those actual size scales are. So just to give you a recap of some definitions that are relevant to understand, basically this is it. Once you have these sort of 6 concepts in, you know everything you need to know about how black holes are born, how they grow, and how we actually detect them, okay? So typically you have the Schwarzschild radius, and then black holes actually grow. I should go back and spend a bit more time on that. So black holes actually grow by the accretion, which is a technical way of saying gobbling gas. They gobble gas from their vicinity, and as gas falls in, because of the high speeds, there's a strong gravity of the black hole, it's accelerated to very high velocities, and it starts glowing in the X-rays. So you see the dying gasps of gas before it makes it into the event horizon come out in the form of X-rays, and we detect that. Okay? And there is some emission, as we'll see, that will also come out in the optical, in the UV, in the ultraviolet wavelengths as well. And we see that too, and that's what quasars are. Quasars are basically very actively feeding black holes, where we are seeing the dying gasps of gas as it makes it in to the black hole. So the typical time scale, the mass doubling time scale for a black hole is what is called the saltpeter time. It's basically 10 million years, 40 million years or so. So that the age of the universe is relevant because that is roughly the ratio between the growth time scale and the age of the universe is what determines how fast you can grow stuff. Of course, you can overfeed the black hole. There's a feeding rate for mass. That's called the accretion rate, and that's proportional to the mass of the black hole. And this luminosity, this energy that is emitted by the gas as it's falling in, that luminosity is actually proportional to the mass feeding rate. And with some efficiency, some small portion of that total rest mass energy of the gas that is falling into the black hole is emitted that we actually detect. And so there is a sweet spot. So there is a luminosity where the gravity of the black hole just about matches the radiation pressure of this gas as it's falling in, and that's called the Eddington luminosity. That's kind of the upper limit of how fast you can feed a black hole. You can circumvent it in certain circumstances in the universe, but for our purposes today, let's not worry about the strange things you can do. Most commonly, this is sort of a cap of the feeding rate for the black hole and therefore for the growth of a black hole. So as I mentioned, there are three numbers that you need to specify all properties of black holes: their mass, their spin, whether they're rotating or not, and their charge. So the charge is not astrophysically interesting for us. So we'll be focusing mostly on the mass and the spin. Okay, so what do we know? As I said, that sweet spot, this luminosity called the Eddington luminosity, which gives you the optimal feeding rate. So when we look at quasars that are bright and they are shining, we detect them at great distances in the early universe. They are growing at the optimal rate, at this Eddington rate. So that's what allows us to infer what the mass of the black hole that is powering that quasar. And it allows us to know that those black holes are 1 billion times the mass of the sun. So what we've started detecting are quasars that are in place, glowing when the universe was only 1 billion years old, 1 billion years after the Big Bang. Which means we need to somehow not just make a black hole, but grow it to be 1 billion times very, very rapidly. So this posed a very big theoretical challenge to theorists like me, but how do you actually do it? And you'll see why this is a conundrum in just a minute. So the energy, this is just to quickly show you that an accreting black hole can actually put out energy in the ultraviolet, so optical light, X-ray, and possibly gamma rays. This is just to show you what all we detect, okay? These are all forms of wavelengths of radiation that we detect from growing black holes. So there's one other cool thing about black holes, which I won't spend too much time on because there are no real observations, and I'm going to really base my talk on bits of the model that we can verify with observational data. So gravitational fields, strong gravitational fields, do some funky things to time, because remember I already said this is a 4-dimensional sheet, space-time. And so a clock for an infalling object into the black hole will slow down compared to a clock held by an observer who is far away. So from the point of view of the person who's falling in, it's going to take them an infinity to actually fall in. Okay? And so this was something that was exploited to great effect in Interstellar. Okay, so what are the challenges? As I said, the key challenges for people like me, theoretical astrophysicists who work on black hole growth, is how do black holes form, how they're actually fueled, how does the gas actually get in, and what impact do black holes have on the environment. And what we are after is looking for observational signatures of all these three concepts, right? Because we're trying to, since black holes on their own don't emit any radiation, we're really trying to figure out how each stage and what observational signatures we could get from each of those stages. And so this is the challenge. So this is a challenge for someone like me trying to couple the physics on different scales, right? So for example, let's take the example of the black hole at the center of our Milky Way. It's 4 million times the mass of the sun. So the Schwarzschild radius for that is the size of the penny, right? And the stellar extent, so this is the entire stellar extent of the galaxy, is the size of the Earth. So it's like putting a penny at the center of the Earth. And the interesting thing is that this penny will have an influence for quite a large portion of not the entire radius of the Earth, but definitely a large portion of it. As you can see, about 1/100th of the size of the Earth's radius could be influenced by the activity of this penny-sized region in the center. And this is very, very challenging in terms of physics to calculate, to say nothing of the cosmological larger scale that this whole thing is embedded in, right? Okay, so what I'm going to now show you is indirect evidence from gas flowing into black holes, and the evidence from motions of stars, and the indirect evidence from their impact on the environment. So, pertinent to the three concepts that I talked about earlier. Just to remind you once again, remember this is what the black hole is doing right in its vicinity. And this is going to be relevant to the kinds of electromagnetic signals, the kind of radiation signals that we're going to get from right around black holes. So first of all, where are black holes? So it turns out, at least from a census of the nearby universe, pretty much every galaxy seems to have a black hole in its center, including our own. So here is a video that starts out with a real Hubble Space Telescope image and then kind of lapses into fantasy and a bit of imagination because we can't quite probe down to the Schwarzschild radius or even 10,000 times the Schwarzschild radius yet. But what this is going to show you is the accretion disk. This is the disk of gas, the feeding disk from which gas falls onto the black hole. And so this is an artist's impression of it, but this gives you a good idea of what the process is. And I'll show you some simulations, real simulations, physics work that actually models the flows onto a black hole. So what are the astrophysical environments? As I said, we find dead black holes that are no longer feeding, they're actually fasting in almost all nearby galaxies, including our own. So these are galaxies whose centers have a black hole that is fed by a very small gas trickle, okay, very tiny, not a quasar, no quasar activity, very small trickle, basically fasting. So these black holes have shut off. So in the nearby universe, most black holes have shut off. And the reason they've been shut off is that there's not enough gas available. So the universe started out very gas-rich, and then a lot of the gas progressively got converted into stars, and some of it made its way into growing the black holes. So by the time we reach today, most of the gas in the universe has been consumed, and the centers of galaxies are pretty bereft of gas. Even spiral galaxies like our own are pretty bereft of gas today. But this is not so in the early universe, as we'll see. And in the early universe, you have these galactic centers that are actively feeding with supermassive black holes, and they are feasting. Okay, so these are the kinds of objects, and we see sort of black holes in these two modes, sort of fasting and feasting. And the idea, obviously, the physics question is, how do you transit from feasting to fasting? What makes you feast? Obviously, it's a supply of gas. The question is, how is it supplied? And how is it efficiently supplied, right? So we have a pretty good understanding of all of that right now. So this is just to show you multi-wavelength data. So what you see on the far left is X-ray data of actually a binary black hole, of two black holes that are actually growing in the center of a galaxy, NGC 6240. And then you have, down in the middle, you have radio data of a binary black hole. And up there, where it looks pretty nondescript, is actually an optical image of an extremely bright quasar, a very distant bright quasar. You can see the arrow, but you can't quite see the red dot, but it's there. So there's now evidence for growing black holes in all these wavelengths. As we just calculated, these are the wavelengths in which you should see them, and you do see them, right? And then let's come to the influence that black holes exert on their environment. And we see that too. So this is the center of a Perseus cluster, which has a black hole that is 1 billion times the mass of the sun, close to 1 billion times the mass of the sun. And then if you actually calculate the energy that is expended as gas is flowing in when it's in the feasting mode, one can actually compute that that energy is almost enough to completely unbind the entire galaxy. So a lot of energy that's given out when a black hole is actually feasting, okay? Even just at the Eddington rate, capped at the Eddington rate. And this is seen in X-ray data. Okay, some other very interesting properties of local black holes that we see are so this is a correlation between the mass of the black hole on the y-axis and the speeds of stars orbiting within the galactic nucleus, the region of influence, within the region of influence of the black hole. And there's a correlation. Okay? And the dots that you see there, the ellipses, give you an idea of the error bars in these measurements. These are measurements for individual galaxies, for about 50 individual galaxies nearby. So part of what we need to understand is why do we have this correlation? These are all dead black holes. They're all fasting. Okay? This is nearby universe. Everything is fasting. So the question is, this correlation, you can intuitively understand that if gas is what is being fed into black holes to grow them, and if gas is what is forming the stars, okay, maybe that's why there's a correlation, right? But we need a better, more physically motivated hunch than that. And so that's what I'm going to show you, what we've developed. But before I do that, let me show you some of the evidence, the strongest evidence for the presence of black holes in the universe. This is the orbits of stars around the Milky Way, center of the Milky Way, where the location of the star symbol marks the position of the putative black hole. And it's the orbits from the closed orbits of this source S2, which is about 17 light hours away from the center, from the black hole. And this is 17,000 light years away from us, the galactic center. You actually can estimate the mass, and that's where the mass estimate for the black hole at the center of our galaxy comes from. Okay, so the question is, so let's come to the formation. How quickly can we make black holes, and what are the masses that we can make them out to be? So as you all probably know, a natural way to make black holes, stellar mass black holes, is to wait for the first generation of stars to form, for them to exhaust all their hydrogen and helium, and leave behind, after an explosion, a remnant black hole. The only problem is, even though the first stars are more massive than the stars that we see forming around us today, the remnants that they leave behind are very tiny. They are about 10 times the mass of the sun to 50 times the mass of the sun. So you still have that growth challenge of growing something that's about 10 to 50 times the mass of the sun at your optimistic Eddington rate within 1 billion years in the early universe and bring it up to 1 billion times the mass of the sun. It's incredibly difficult, okay? So what that tells you is that there has to be more than one way to make black holes, right? So the other fact that we know, the data that we know, is shown in the schematic here, which shows you that the number of actively growing black holes peaks at a particular time in the universe and then starts falling. Okay? So if you see now, there are very few active quasars. They're all dead black holes, as we just saw. So okay, here are the three different pathways that we now believe lead to the formation of the first black holes, the seeds. So the population 3 is just a fancy name for the first generation of stars. That will give you some stellar remnants. Then you can form a cluster of stars that will all die and leave little black holes that will merge and give you a bigger mass seed. Or what I think is my favorite method, not just because I worked a lot on it, is the formation from the get-go of a very massive black hole seed, something that is about 10,000 to 100,000 times the mass of the sun from the get-go. And this is what we call a direct collapse black hole. And this gives you a schematic of this idea. And with one of my postdocs, Giuseppe Lodato, almost 8 years ago now, we kind of worked out this scenario to see if it was viable. And it turns out that it is actually viable in the sense that the kinds of physical properties you need for this process to occur are available in the early universe. They are rare sites, but they are available in the early universe. So what really happens is you have the assembly of a pre-galactic gas disk. So you form a gas disk before any stars form in the early universe, and this gas disk becomes unstable, and all the mass from the disk, instead of fragmenting, makes it down to the center, much like the vortex that is generated in your bathtub when you unplug it. So stuff starts moving very rapidly inside, and you assemble something that is extremely, very, very massive black hole seed. So these are the direct collapse black hole seeds. So obviously, what we would like to know is whether there are observational ways in which we can discriminate whether a black hole that you see downstream that is 1 billion times the mass of the sun or 1 million times the mass of the sun, whether it came from a direct collapse black hole seed or whether it came from a very tiny seed that grew remarkably steadily for a very long time. Obviously, the black hole itself does not contain any information on how it was born. So we are going to rely on these correlations and the properties of the black hole and the galactic nucleus that it lives in to discriminate these models, as we'll just see. So the direct collapse black holes, we note, would form in a satellite galaxy in the very early universe. So you have a very massive galaxy that has formed stars already and is letting out radiation. The purpose of this, it would be irradiating this little satellite. It would prevent gas from cooling and forming stars and would form a direct collapse black hole instead. Now this little proto-galaxy that has formed a direct collapse black hole will immediately merge. So merging is ubiquitous in the universe, especially in the early universe. All structure in our universe assembles hierarchically from the merging of smaller units. So small galaxies merge, small galaxies with little black holes in their centers. Not all of them may have black holes, some may have black holes, would merge and then give you bigger galaxies. So a direct collapse black hole, because there are no stars forming right around it, it will merge and it will acquire its own little constellation of stars. But what is interesting about direct collapse black holes is that the mass of the black hole will outweigh that of the stars, contrary to what we see in the nearby universe in that correlation plot that I showed you, where the mass of the black hole is tiny compared to the mass of the stars. So there will be a period in the early universe where the mass of the black hole will exceed the stellar component that it is sitting in, the nucleus that it is sitting in, and the radiation emitted by the black hole will dominate that of the stars. And so this is a signature that we have just predicted, and what you see there is the predicted spectrum of such an object that can be seen. It'll be booming and it'll be detectable by the James Webb Space Telescope that is due to fly in 2 years. So if we find objects that look like that, and normal galaxies where the starlight dominates the black hole will have the shape of the spectrum shown in blue there. Notice that you can easily discriminate the shapes of these spectra with the instruments that are going to be aboard the James Webb Telescope. So let's now try to get to the nitty-gritty of the physics of how actually black holes grow and what the feasting episodes look like. So as I said, much of the feasting happens when gas, during the merger of two galaxies, is pushed to the center, reaches the center, and you can start overfeeding the black hole. And as I said, the other mode for feeding a black hole, which is probably the fasting mode, is a very slow and steady trickle that is quite inconsequential in actually building up the mass, but it's something that continues over cosmic time. So this is just a slice, a sideways slice of an accretion disk, and the black hole is sitting right at the center of where you see those two beaks meeting. This is a slice through an accretion disk. And what the color coding here is telling you about the temperature and the density of the gas. And the gas right from the center is going to fall onto the black hole and going to be accreted. So now there's a beautiful video from NASA, which I want to show you. It's a computer simulation performed by a group based at Johns Hopkins and NASA Goddard Center, where they actually show you the flows, the precise flows that I've been talking about of the gas and how they make it close to the Schwarzschild radius. And what you see here swirling is the turbulent flow of gas, and the color coding is a temperature and density. And you'll see that you can see the rim. That rim is the Schwarzschild radius and the photon sphere around which you can see emission. So the density square of gas is what gives you X-ray emission, and so what you're seeing here is the X-ray view in soft wavelengths for what you should see from the accretion disk. So this is how black holes are revealing themselves, right? So this is a computation that actually shows you and helps you interpret the X-ray data that we actually have in hand from the Chandra Space Telescope. And you can see all the features and the scales that I talked about marked really beautifully in this movie. And it turns out that very close to the center, the material is accelerated and is almost at half the speed of light. And there's a Doppler shifting from the far end and the near end of the black hole. And so it's the corona, the outer region, the more extended region from which you see very hard, very strong, the most energetic X-rays come out of. And what's very nice about the schematic is it gives you an idea of the viewing angle and how the viewing angle matters in terms of what kinds of emission you're actually going to see. So for example, when a jet is emitted by the black hole, material and energy are flung out from the center unless the jet is really facing you or you're within a cone of influence of the jet, you will not see the jet. And that's what, but we do see a lot of jets. But when we look at the frequency of jets, we have to factor in the visibility and the angle to figure out how frequently black holes are actually pushing out jets. Okay, so as I said, accretion growth episodes for black holes are triggered by mergers of galaxies. And we see galaxies merging both much more fiercely so in the distant universe and at lower rates in the nearby universe. Okay? And so these are Hubble Space Telescope images of some very dramatic mergers that I will just show you a theoretical calculation that shows you how gas flows during the merger process are going to be helpful to feed the black hole. So this is a slice, a static slice from a cosmological simulation, which is all gas. And what you see is filamentary flows of gas. And the places where filaments intersect are places where the galaxies form, and that's where black holes form. So these two regions that are marked in green are basically going to be two galaxies whose merging we are now going to follow with a zoom-in simulation. So this is a simulation where we start out with these two very gas-rich disks. So you're seeing the gas in blue. And if you notice the center, it's flickering. But it's flickering proportional to the feeding rate. So it's giving you an idea before things merge how they're feeding the black holes, the individual black holes. Both these galaxies, spiral galaxies, are populated with central black holes. And so you will see that they are bound. They will have many passages before they completely disrupt. And at the end, you will have one big black hole whose mass will be slightly less than the sum of the two black holes. And the reason for that is some portion of that mass will actually be emitted in gravitational waves. As we just saw, in the case of LIGO, we saw the merger of two stellar mass black holes giving you gravitational waves that were detected. In the case of supermassive black holes, you would get gravitational waves too. And interestingly, you would, because this would happen in the gas-rich environment of the center of a galaxy, in addition to just the gravitational waves, we'll get a lot of other electromagnetic signatures. There'll be heated gas that will be expelled. There could be a flash. There would be a transient that would come that we could measure in the X-rays or in gamma rays. So the interesting thing about supermassive black hole mergers, and it's called multi-messenger astronomy, is that you will have a lot of multi-wavelength effects that you can detect, which will help you pin down where the gravitational waves came from. So one of the interesting things that you might have seen in Ray's talk earlier today is localizing where the LIGO event came from in our galaxy. It's like a huge region. They can't actually pinpoint where it came from. For supermassive black holes, as and when they merge, because we expect a lot of counterpart electromagnetic signatures to be produced, we're likely to be able to pin them down. Of course, we are yet to detect the gravitational waves from these supermassive black holes. So I wanted to show you, we are zooming right in to try and understand how the merger of two supermassive black holes actually happens. So what you're going to see here in this movie, when you start the video, is we are looking top down on an accretion disk. There's a very massive black hole in the center where you see the cutout, and you have a secondary that is plowing in. And you can see that as the secondary makes its way in, it sets up all these waves in the disk. It sets up these modes in the disk, these perturbations in the disk, which will come out as perturbations in the luminosity of the accretion disk. And so we should be able to see it happening. The one other interesting feature here that you'll see is that you see this black region. So what it has really done, if you look at the inset was a side profile of the disk to start out. And so could we play this video again, please? This is the side profile of the disk, and we are looking at it top down. But notice as the secondary is moving in, it starts pushing down the inner region of the disk. And then as it's plowing in, notice it's causing a real dent in the disk. it opens up what is called a gap in the disk. And it evacuates the region of gas. It decouples the inner region of the disk from the outer region of the disk. And all the gas that is stuck in the inner region will have no place to go but on the final black hole. So you will see a huge quasar as soon as a black hole merges with two supermassive black holes. So our current understanding is this is the life cycle of a supermassive black hole and the relationship to quasars, that you have two very gas-rich galaxies merging at very early times. You feed the black hole, you have the dance that we just saw in the simulation, and then you generate a very bright quasar at the end of it. And we believe that the most massive black holes in the universe likely had this life cycle. And with the data and with our models, we're actually able to even pin down the time scale for which these stages would last at the moment. Right? So this is what is happening inside the merger. So essentially you have what is a circumbinary disk, a gas disk that encapsulates both the black holes, and as the primary and the secondary are plowing towards each other, they may have their own individual disks that may or may not survive, and eventually, this is how you end up seeing, you have a huge accretion rate, a very strong accretion rate at the merger, you have gravitational waves, and you have a huge amount of emission coming in the optical, the X-ray, and so on and so forth. So what recently happened with LIGO was there was a breakthrough in the computation in the combining of the hydrodynamics, that is the properties of the gas that is around, and the regime close to the Schwarzschild radii, where general relativity and general relativistic effects become very important. So as I told you, this is a computationally a very challenging problem to bridge the scales, but there was a breakthrough. In fact, this breakthrough is what enabled people in the LIGO collaboration to pin down the event, the template for the event. And this was done for stellar mass black holes, right? And of course, I love this movie that shows you roughly the effects, again, on light propagation that the presence of the black hole and the mergers of the black hole would do, and what the sky behind those black holes would look like. And that was a real image of the real night sky, roughly in the location where the LIGO event happened. Right. And of course, the shaking of space-time, the tremor is hugely exaggerated here, right? As you know, it was a very challenging, tiny measurement, high precision measurement. So this particular waveform, right? So this shape of the waveform for the sort of, as the merger proceeds of black holes, this was computed, the template was computed very recently. For decades, people could not solve this problem of bridging the scales. And there was a breakthrough about 5 years ago. And it's the ability to template it that allowed them to actually find the event, right? So such templates have now been made for supermassive black hole mergers. However, the instrument is not LIGO. It's a different frequency. And the instrument that we hope to have in the future is an interferometer much like LIGO, but in space. Because that's the kind of sensitivity, we need much lower frequencies. There will be much lower frequency events than the LIGO event that we just saw. But we believe that the event rate, that these mergers, as I told you, are ubiquitous at early times. And there is no loss as for gravitational waves as they make their way to us, right? They're just going to get, we're going to see the flux. So no matter where the event occurred, we're going to see the flux, unlike optical light, right? So, so this is where the future is. And hopefully, if after LIGO, there has been excitement generated enough in the scientific community, definitely is excited. But whether the funders, in particular NASA, will join in with the Europeans. There's a prototype called ELISA that is currently flying, and it's testing out parts of the technology. It's a very, very technically challenging measurement to make. I mean, it was incredibly technically challenging to do from Earth, so you can only imagine what it's like from space. But I think this is where we are at. So it's the combination of the instruments aboard the James Webb Space Telescope that will uncover the first black holes, the early black holes, that will help us discriminate between direct collapse formation scenarios and formation from stellar mass black holes. And then this whole picture of things driven by mergers and this whole story that I just sort of outlined to you in the cosmic context of how black holes fit in terms of the stellar component that they inhabit in the centers of galaxies, that stands to be tested with LISA. So I'll just stop here and open up for questions. Thank you.